Welcome to this explainer. Today, we are definitely not treating the Cambridge AS and A-level physics syllabus like some dusty, boring textbook. Instead, we're looking at it as a matrix of predictable patterns just waiting to be decoded. If you've ever stared down a uniformly accelerated motion problem, that intimidating wall of random numbers, and felt completely lost, well, you are in exactly the right place. We're going to crack the code on Physics 9702 today. Let's decode those famous SUVAT equations together. Okay, let's take a look at this opening quote right here. This actually reveals a massive secret about how examiners are truly grading your paper. Memorizing the formulas? Yeah, that simply isn't enough anymore. The examiners are actively hunting for the underlying code of your conceptual understanding. They don't just want a human calculator, right? They want to see if you really grasp the why and the how. That way, you can easily adapt when they inevitably throw a completely unfamiliar context at you on exam day. So here is our blueprint for today's explainer. We'll take you systematically through first the core theoretical framework, then executing the standardized sequence, and finally, the top examiner mistakes avoided. Let's jump right in. All right, phase one, the code. Let's decode the core theoretical framework that forms the whole architecture of these questions. Now, the absolute crucial point here is that SUVAT, which as we know stands for displacement, initial and final velocity, acceleration, and time, it really isn't just a basic math exercise. These equations of motion form a deep conceptual framework. The syllabus actually demands your mastery of fundamental principles and causal relationships. So when you see a falling object in freefall, don't just immediately reach for your calculator. Take a breath and establish the theoretical physics at play first. And this is brilliantly illustrated by what principal examiner reports highlight year after year. The absolute top candidates, they form cross-topic connections. They achieve significantly higher marks because they never treat SUVAT as just an isolated island. They actually link these kinematics to dynamics, analyzing the actual physical forces that are causing the motion in the first place. Drawing those cross-topic connections is exactly what unlocks the highest grade boundaries for you. Moving on to phase two. Executing the standardized sequence. Because knowing the code is one thing, but running it on paper, that's where the marks are actually won. Now, what's really fascinating here is that examiners literally look for this exact 5-step standardized sequence when processing SUVAT problems. Step 1, identify the key elements. Step 2, apply the relevant principles. Step 3, execute the analysis with crystal clear working. Step 4, verify those results. And finally, Step 5, present it in the proper format. Honestly, if you skip around or just jump straight to the final answer, you're leaving your final grade completely up to chance, and we definitely don't want that. This brings us to an absolute game changer, straight from the senior examiners themselves, the method mark strategy. Showing clear working literally saves your grade. Let me be totally clear on this. Under intense exam stress, you might accidentally punch the wrong numbers into your calculator. It happens to the best of us. But if your process is systematically laid out on the page, method marks act as your safety net. They'll catch you and earn you points even if that final number is dead wrong. So, how do you lock in those precious method marks? You utilize the deconstruct, solve, evaluate loop. Identify the given information, break it into logical steps, solve it systematically, and then, here is the absolutely critical part, evaluate it for reasonableness. Think about it. Does a standard everyday car really accelerate at 5,000 meters per second squared? Probably not, right? This loop forces you to step out of pure abstract math and actually ground your physics calculations in reality. Furthermore, your presentation on the page has to follow these strict conventions. Think of it as the proper syntax for your exam code. You need proper structured headings, precise scientific terminology, correct appropriate formats, and readable annotation. If your sheer brilliance is hidden behind chaotic, messy handwriting, the examiner physically cannot award you the marks. Structure your answers so the logic practically jumps right off the page. All right, let's explore phase 3, the glitches. It's time to uncover the top examiner mistakes avoided. A deep dive into the examiner reports reveals that there are exactly 3 primary mistakes that consistently cost students their hard-earned grades in uniformly accelerated motion. Let's go ahead and patch these glitches right now. The first massive glitch, vague answers. You see, examiners are actively hunting for highly specific details. Don't just vaguely write that a value increases or that a force changes. You've got to specify exactly how it increases, note the specific rate, and point to the exact evidence in the data. Broad generalizations, they earn 0 marks. Specificity is your absolute ultimate currency here. And as you'll see here, glitches 2 and 3 follow closely behind that vagueness issue. Number 2 is simply forgetting to check your format and presentation, basically ignoring your syntax. And number 3 is failing to ground your math in the specific context provided by the question. Your answer absolutely has to make sense for the actual physical scenario described in the prompt. It can't just exist as some abstract number floating in space. Now, here is a very specific context warning. When a SUVAT question asks you for a comparative analysis, a seriously flawed approach is just listing the similarities. A perfect comparison, on the other hand, identifies both similarities and differences. It uses proper comparative connectives, and it draws firm conclusions backed by evidence. Please don't just give them half an analysis. Deliver the complete comparative picture to secure those marks. So, how do we avoid these pitfalls entirely? Well, the sources suggest a pretty powerful memory hack. Formulate a personal acronym. Whether it's to help you remember the execution sequence we talked about or the formatting conventions, tying these strict requirements to an acronym ensures you never, ever leave a single method mark behind in that exam hall. It's a real game changer. So, we've built the framework, outlined the sequence, and patched the glitches. The next time you face a uniformly accelerated motion problem, are you going to fall into the old trap of blind memorization? Or will you apply the deconstruct, solve, evaluate loop and finally see the underlying code behind the question? The choice is entirely yours. Keep decoding, keep practicing, and we'll see you on the next explainer.